So now here's a circuit I think is pretty cool. I based it off of the LM358 datasheet from Texas Instrument. This is a 358 dual op amp from a different manufacturer, but it should work exactly the same. So let's just show what it does at first. So when I turn the dial here, the trim pot here, more towards the negative rail so that it outputs 0 volts. That's the green jumper, but I also have this yellow jumper there so we can measure the voltage. Because this has pins that go right into the board, there's nowhere to measure it. If I turn it more positive, you see that the LED gets brighter. And at some point it's going to stop getting brighter before we get to the rail. And we'll look at that coming up. But in any case, this is a voltage divider. It is giving the op amp, the non-inverting pin, the bottom one here. It's a dual op amp. We got one on the left side, one on the right side. We got the non-inverting, the inverting, and then the output. The output is where that jumper is there, third pin up. And so the voltage that we give, since we are using a 1 kilo ohm resistor, this is the 2N2222 NPN bipolar junction transistor, wired as an emitter follower. So we have a 1 kilo ohm resistor the way we have it wired up. For every volt we give to the non-inverting input, the 2N2222 will pass 1 milliamp of current because it's a 1 kilo ohm resistor, as I said. So we can just go to any random voltage. Let's go there first. Let's measure the rail voltage, and we will see 15 volts at the rail there. So slightly less than 15. Let's turn it up just a little bit. I don't like always being a little bit below the number. I'd rather be a little bit high. So there you can see a little bit higher. There you can see 15 volts there. Now what we're going to do, we're going to look at the trim pot voltage. So I have that jumper at the trim pot output. We have it set to 6.37 volts. So I expect 6.37, pretty much spot on milliamps of current going through the LED. So 6.37. So let us pull that jumper out and then set the meter to measure milliamps. And what we can do is just put the red probe to this jumper, which goes to the positive rail, and now complete the circuit. And there you can see 6.39. So we had 6.37 volts. This is 6.39 milliamps of current. And so we are basically spot on right there, and just a speck different. So let's also look at really quickly while we are here that we won't get up to 15 milliamps of current. From earlier testing I found we get about 12 milliamps of current, and then that's where it reaches its limit, about 12.5. And so I raised the voltage a little bit, but now you can see we did get 13, and but as I get more towards the positive rail, it dips back down to 12.2. And before I raised the voltage, we reached the limit of 12.5. But there you see, we can't get to 15 milliamps. It doesn't go all the way to the positive rail, but it goes the vast majority of the way there. So let's take this apart, build it up step by step. I don't have a schematic for this one yet, but it's really not that complicated. So now up here we have the first, let's do the LED, why not? And so of course that side's more positive, and so that's where the anode, the long lead of the LED goes. And then we put the short lead, the cathode, down there, the transistor, and the resistor will be what limits the current. And we got the 2N2222 right here. Left pin is the emitter, middle pin is the base, right pin is the collector, and the base is the pin that controls how much current ultimately flows through the transistor. And current flows positive from the collector to negative at the emitter. So you can see those are the sides of the circuit that the power supply is wired up. So it flows through there. Current flows from a supply through the LED to the collector, and then from collector to emitter based on what we are getting at the base. So you can see the base, the middle pin, that comes to the output of the 358 op amp right there. And so it outputs what it needs to based on the signals that we give. So we have a jumper that goes to the inverting input, and I'm giving a signal that's really sensitive. That is setting that off. That's the problem there. And we're going to put it on the same row. We could put it here, but that kind of blocks things. We'll put it on the same row as the where the resistor is and the emitter. So what it's doing is, ultimately, it's looking at the voltage at that point. And so what it's doing is it's outputting what current it needs to get that voltage to the same voltage as the non-inverting input. That's ultimately what is going on. So now we will zoom back, and that is, if we looked at it, there'd be a waveform, probably like a sine wave, because it's picking up stray signals from power in the house. So we take this jumper here, and so this is how we're given the voltage that we set the trim pot. So the middle pin there is the output. I also added that wire there. I could just plug it right there even, but in any case, we plug it there, and now we have the voltage that we have the current set from the voltage coming from the trim pot. So let's turn that down. You see it gets darker, and the brightness didn't change when we plug that in, but you see when we remove that, now it's stray signals triggering it. Now it is the trim pot that is doing it. So let us do a low reading. That's pretty low current, maybe 2 milliamps or so. And as I said before, the amount of current per voltage depends on the resistor you use. So what the op amp and transistor are doing, the way that we wire it up here, as I said, is holding the voltage there the same as the voltage that we set. So we set the voltage to oops, I have the probes backwards. That's the problem. So actually it's quite a bit lower than 2 milliamps. It's a 0.69, so about 0.7 volts, I mean not amps, 0.7 volts. And so if we measure the current, it should be about 0.7 milliamps, because it's a 1 kilo ohm resistor. And we got to get that to the positive rail, and then that one to the LED. And there you can see 0.69 milliamps. It was 0.69 volts right here. Now, what we can do is yank the 1 kilo ohm resistor, and this is a 510 ohm resistor. And no, that's the 100. That's another 1000, I think. There we go, 510 ohm resistor, and put that to the rail. So it starts with green. That's how I know it's 500. And now we will measure the current, and it should be twice. So it was 0.69. Now it should be 1.28. About that exactly. And oh, I put that to the positive rail. That's the problem. There we go. But there you can see 1.36. So I estimated about 1.38. And the main thing though, there's also 510 ohms, not 500. But in any case, that was definitely close enough. It's pretty much spot on. So this is a pretty fun circuit in my opinion. And we just take the voltage in, and using the op amp, in this case the 386 op amp, we get an output, a programmable output based on the voltage. With a 1 kilo ohm, it makes it really easy. It's 1 milliamp of current for every volt that you give. It will give that to any load, as long as it doesn't have too much resistance and voltage drop within it. So, hope you found the video interesting. Thanks for watching. I will see you in the next video.